Welcome! In this session, we'll explore an interesting problem titled Count Fertile Pyramids in a Land. We'll break down the problem requirements, discuss potential approaches, and analyze their efficiencies. Let's dive in and solve this step by step. In this problem, you are given a binary grid that represents a piece of land. Each cell in the grid is either a 1, indicating that the cell is fertile, or a 0, indicating that it is not. The task is to find and count all pyramids and reverse pyramids that can be formed using the fertile cells. A pyramid is defined as having a triangular shape, with its base being a horizontal line of cells and the apex at the top. The base has a length of 2h1, where h is the height of the pyramid. Every row above the base must be narrower than the row below it, shrinking by one cell on each side. Similarly, a reverse pyramid has the same structure but is inverted, with its base at the top and apex at the bottom. The goal is to write a function that returns the total count of both pyramids and reverse pyramids in the grid. The output of the function is a single integer, which is the total number of pyramids and reverse pyramids present in the grid. Let's go through an example to better understand the problem. Suppose the input grid is as follows: 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0. In this case, the output would be 2. This means there are 2 pyramids or reverse pyramids present in the grid. We'll now explain why this is the case. In this grid, there is 1 pyramid and 1 reverse pyramid. The pyramid has its apex at cell 1, 2, and extends downwards with a height of 2. Similarly, the reverse pyramid also has its apex at 1, 2, but extends upwards with a height of 2. In another example, consider a grid where all cells are 1, such as 1, 1, 1, 1, 1, 1, 1, 1, 1. Here, the output is 6, because multiple pyramids and reverse pyramids can be formed. Specifically, there are 2 pyramids and 2 reverse pyramids of height 2, and 2 additional pyramids of height 1. Now consider an example where the grid is 1, 0, 1, 0, 0, 0, 1, 0, 1. In this case, the output is 0, meaning no pyramids or reverse pyramids can be formed. This is because there aren't enough consecutive 1s in any row to form a valid pyramid base, and the configuration of the 1s in the grid does not allow for the triangular shape required by the problem's definition. Finally, let's discuss some constraints and additional notes. The grid has dimensions mxn, where m and n can both be as large as 100. Each cell in the grid is either 0 or 1. The height of a pyramid or reverse pyramid must be at least 1, and while pyramids and reverse pyramids can overlap, they are still counted as separate structures. Given the maximum grid size, it's important to ensure that your solution is optimized to handle large inputs efficiently. Make sure to consider all these details when implementing your function. When tackling this problem, we first considered a brute force approach. The intuition here is straightforward. For every cell in the grid, we check if it can serve as the apex of a fertile pyramid. To do this, we evaluate pyramid height starting from 1 and going up to the maximum possible height for that cell. For a pyramid of height h, its base would require a width of 2h1, and all rows below the apex must have enough fertile cells to form this triangular structure. While this approach is conceptually simple and easy to implement, it comes with significant drawbacks. The worst-case time complexity is m times n times h squared, where m and n are the dimensions of the grid, and h is the maximum height of a pyramid. This means that as the grid size or potential pyramid height increases, the computational cost quickly becomes prohibitive, particularly for larger inputs. This inefficiency led us to explore a more optimized solution using dynamic programming. In the optimized dynamic programming approach, the key insight is that the height of a pyramid at any given cell depends only on the row directly below it. This allows us to avoid redundant checks and achieve better efficiency. We define dp, ij, as the maximum height of a pyramid with its apex at cell, ij. If the cell itself is fertile, i.e. grid, ij, equals 1, then the height of the pyramid at that cell can be determined using the recurrence, dp, ij, equals 1 plus min, dp, I plus 1, j1, dp, I plus 1, j, dp, I plus 1, j plus 1. This formula ensures that the current cell can only support a taller pyramid if all 3 supporting cells in the row below also have sufficient capacity. On the other hand, if the cell is not fertile, the height is simply 0. By iterating from the bottom row to the top, we can compute the DP values for all cells in O(m*n) time. Once the DP table is populated, the total number of fertile pyramids can be obtained by summing all the values in this table. This method is not only efficient, with O(m*n) time complexity, but also flexible. For example, to count inverted pyramids, we can apply a similar DP approach, but iterate from the top row downward. By combining counts for both upright and inverted pyramids, we can calculate the total number of fertile pyramids in the grid. The optimized dynamic programming approach emerged as the best strategy for this problem due to its balance of efficiency, scalability, and clarity. The key realization that the height of a pyramid depends only on the supporting row below was pivotal, as it allowed us to eliminate redundant checks and drastically reduce computational overhead. For large grids, this approach is far more practical than the brute force method, which, while conceptually simple, is computationally infeasible for larger inputs. Moreover, the DP solution is highly flexible. It can be extended to count both upright and inverted pyramids with minimal additional complexity. This makes it not only the most efficient but also the most versatile approach to solving the problem. While the brute force approach provides a clear understanding of the pyramid construction process, the dynamic programming strategy stands out as the optimal choice for tackling this problem effectively. In this problem, we are tasked with identifying fertile pyramids in a grid. A pyramid is defined as a triangular structure where the topmost cell, or the apex, sits at the peak, and each subsequent row below it expands symmetrically, forming a triangle. To determine if a pyramid is valid, we need to ensure that the apex and all rows below it contain enough fertile cells to support the triangular structure. For a pyramid of height h, the base of the pyramid will have a width of 2h1. This means that each row below the apex must have one additional fertile cell on each side compared to the row directly above it. Keeping this in mind, it's critical to understand these constraints for identifying and counting valid pyramids in the grid. Now, to efficiently check for these pyramids, we begin by pre-computing information about the fertility of the grid. The input is a 2D grid where each cell is either fertile, represented as 1, or barren, represented as 0. The goal is to create two helper arrays, left and right, which store the number of consecutive fertile cells to the left and right of each cell, respectively. This pre-computation is useful because it allows us to quickly verify if a row meets the conditions for forming part of a pyramid. To build these arrays, we iterate over each row in the grid. For each cell, we calculate the number of consecutive fertile cells to its left and store it in left, I, j. Similarly, we calculate the number of consecutive fertile cells to its right and store it in right, I, j. By storing this data for all cells, we eliminate the need to repeatedly calculate fertility for each potential pyramid, making the process much faster. Next, we use the pre-computed left and right arrays to identify and count all valid pyramids. For each fertile cell in the grid, we attempt to construct a pyramid with that cell as the apex. To do this, we iteratively check if the rows below the apex satisfy the fertility conditions for a pyramid of increasing height. Specifically, for a pyramid of height h, the base must have a width of 2h1 fertile cells. Using the left and right arrays, we can quickly verify if there are enough fertile cells on each side of the row to support the pyramid. If all rows meet the conditions up to the current height, the pyramid is valid, and we increment the count. To optimize further, if any row fails to meet the conditions, we stop checking for greater heights, as larger pyramids will also be invalid. This approach ensures we efficiently count all pyramids while minimizing redundant computations. Finally, let's analyze the complexity of the algorithm and address potential edge cases. The pre-computation step, where we calculate the left and right arrays, takes O(m*n) time, where m and n are the dimensions of the grid. Checking for pyramids involves iterating over each cell and attempting to build pyramids up to their maximum possible height, resulting in a worst-case time complexity of O(m*n)h, where h is the maximum pyramid height. Since h depends on the smaller dimension of the grid, this complexity is manageable for reasonably sized grids. Edge cases to consider include small grids, where the dimensions may not support a pyramid of any significant height, grids with no fertile cells, which should return 0, and grids with scattered fertility patterns, which require careful validation. By handling these scenarios, the algorithm remains robust and efficient across various inputs. Here, we define a Python class solution with a method countPyramids, which takes a grid as input. The grid is a 2D list representing the land, where fertile cells are marked as 1 and barren cells as 0. First, we determine the number of rows and columns in the grid. Then, we define a helper function count_in_direction to count pyramids in a specific direction. Inside this function, we initialize a dynamic programming table, DP, to store pyramid heights at each cell, and we also initialize a counter to track the total number of pyramids. For each cell in the grid, we check if it is fertile. If it is, we calculate the pyramid height at that cell. For cells not in the first row, we check the 3 cells directly above it, left, center, and right, to determine the minimum height among them, adding 1 to form a pyramid. Otherwise, for cells in the first row, the pyramid height is simply 1. We then update the count of pyramids by adding the height of the current cell -1, which accounts for pyramids beyond the smallest single-cell ones. Finally, the function returns the total count of pyramids in that direction. Using this helper function, we first calculate the number of pyramids facing upward by passing the original grid to count_in_direction. Next, we reverse the grid to prepare for counting downward-facing pyramids. After reversing the grid, we call the same helper function count_in_direction to calculate the number of pyramids that are facing downward. The reversed grid allows us to treat downward-facing pyramids as if they were upward-facing from the perspective of the algorithm. Once we have both the upward and downward pyramid counts, the total number of pyramids in the grid is simply the sum of these two values. Finally, the method returns this total count, providing the result for the problem. Here, we start by defining the countPyramids method, which takes a 2D grid as input. This grid represents the land, where each cell is either fertile, indicated by a 1, or barren, indicated by a 0. First, we determine the number of rows and columns in the grid, as these dimensions will be critical for our calculations. Next, we define a helper method named countInDirection, which will calculate the number of pyramids in a single direction, either upward or downward. Inside this method, we create a 2D array DP to store the maximum height of a pyramid that can be formed at each cell. We also initialize a variable count to keep track of the number of pyramids. The nested loops iterate through each cell in the grid. If the current cell is fertile, we calculate its potential height as a pyramid top by checking the cells directly below and diagonally below it in the previous row. Using the math.min function, we ensure the pyramid height is limited by the shortest base it can form. If the cell is not part of a larger pyramid, it defaults to a height of 1. Finally, we increment the count by dp, rc1, as we subtract 1 to exclude the base level of the pyramid. This ensures that only true pyramids, not single cells, are counted. Now that we've implemented the helper method, we use it to count pyramids in 2 directions. First, we call countInDirection on the original grid to calculate the number of upward-facing pyramids. To count downward-facing pyramids, we reverse the grid. This involves creating a new 2D array, reversed grid, where each row in the original grid is flipped vertically. By passing this reversed grid to the helper method, we calculate the number of downward-facing pyramids. Finally, we return the sum of upward count and downward count, which gives the total number of fertile pyramids in the land. This approach ensures that we account for all possible pyramids efficiently, leveraging dynamic programming to minimize redundant calculations. Here we start with a small 3x3 grid where no pyramids can form. First, we analyze the input grid, which contains a mix of 1s and 0s. The dimensions of the grid are determined to be 3 rows and 3 columns. To begin solving the problem, we initialize a dynamic programming table, or DP, with all 0s. This table will help us track the height of upward pyramids at each cell as we process the grid. The goal here is to iterate through the grid and count the number of upward pyramids that can be formed. Now, we process the first row of the grid. At cell 0, 0, the value is 1, so we set dp 0, 0 to 1, indicating the start of a possible pyramid. Similarly, at cell 0, 2, the value is also 1, so we set dp 0, 2 to 1. The updated DP table reflects these changes. Moving to the second row, at cell 1, 1, we again find a value of 1. To determine if this can be the apex of an upward pyramid, we check the DP values of the 3 cells directly above it, dp 0, 0, dp 0, 1, and dp 0, 2. Since the minimum of these values is 0, no pyramid can form with a height greater than 1 at this position. We update dp 1, 1 to 1, and the table reflects this adjustment. In the third row, we find that no pyramids can form because the surrounding cells contain zeros, preventing any upward pyramid formation. At this point, the count of upward pyramids is 0, as there are no cells in the dp table with a value greater than 1. Next, we reverse the grid and repeat the same process to count downward pyramids. After evaluating the reversed grid, we find that no downward pyramids can form either. Therefore, the final output for this example is 0, as no pyramids of any type exist in the grid. Now we move to a new example with a fully filled 3x3 grid, where all cells have a value of 1. In the first row, all cells are set to 1 in the dp table, as each can form the base of a potential pyramid. The updated dp table reflects these values. In the second row, we examine cell 1, 1. Here, the values of the three cells directly above it, dp 0, 0, dp 0, 1, and dp 0, 2, are all 1. Taking the minimum of these values and adding 1, we calculate dp 1, 1 to be 2, indicating that this cell is the apex of a pyramid with a height of 2. The dp table is updated accordingly. In the third row, we analyze cell 2, 1. The three cells directly above it, dp 1, 0, dp 1, 1, and dp 1, 2, have values of 0, 2, and 0, respectively. Taking the minimum of these values and adding 1, dp 2, 1, is updated to 1, reflecting the formation of a smaller pyramid at this position. At this point, the count of upward pyramids in the grid is 2, as indicated by the heights in the dp table. To count downward pyramids, we reverse the grid and repeat the same process. After evaluating the reversed grid, we find that there are 2 downward pyramids as well. Combining the counts of upward and downward pyramids, the total number of pyramids in this example is 4. For the final example, we examine a grid where all cells are 0. Since no fertile land is available, no pyramids can form, and the output is 0. This demonstrates how the algorithm handles cases with no fertile cells effectively. To understand the time complexity of our solution, we can start by analyzing the operations within the count_in_direction function. This function has 2 nested loops that iterate through each cell in the grid. If the grid has rows and calls columns, this means we perform rows*calls iterations in total. Inside these loops, we calculate the value of dp, r, c for each cell. This involves a constant time operation where we take the minimum of 3 neighboring dp values and add 1. Since this computation is done for every cell, it also contributes rows*calls to the total complexity. Additionally, the function count_in_direction is called twice, once for the original grid and once for the reversed grid. Reversing the grid takes rows time, which is negligible compared to the rows*calls operations. So, the dominant factor in our time complexity comes from the nested loops and the dynamic programming calculations. When we combine the operations from both calls to count_in_direction, we get an overall time complexity of rows*calls for processing the original grid and another rows*calls for processing the reversed grid. Adding these together results in a total time complexity of rows*calls plus rows*calls, which simplifies to rows*calls. Now, turning to space complexity, the primary contributor is the dynamic programming array dp, which has the same dimensions as the grid, requiring rows*calls space. Additionally, we allocate space for the reversed grid, which also requires rows*calls storage. These 2 components dominate the space usage of the algorithm. Apart from the dp array and the reversed grid, the algorithm uses a few other variables such as count, rows, and calls, which take constant space, or O1. When we combine all these contributions, the total space complexity becomes rows*calls for the dp array plus rows*calls for the reversed grid, resulting in an overall space complexity of rows*calls. Compared to a brute force approach, this optimized solution is significantly more efficient. A naive approach would involve iterating through all possible pyramid sizes for each cell and checking if each pyramid is valid. This would lead to a time complexity of approximately O rows asterisk calls asterisk min rows calls, as the pyramid height is limited by the smaller grid dimension. In contrast, our dynamic programming approach computes the maximum pyramid height for each cell in constant time, reducing the time complexity to O rows asterisk calls. Analyzing the best, average, and worst cases, we find that the algorithm consistently maintains a time complexity of O rows asterisk calls. In the best case, where all cells are infertile, 0, the algorithm still processes every cell once, resulting in O rows asterisk calls time complexity. In the average case, the distribution of fertile cells, 1, might vary, but since the complexity is determined by the grid dimensions, it remains O rows asterisk calls. In the worst case, where all cells are fertile, 1, the algorithm performs the maximum number of computations, yet the complexity still simplifies to O rows asterisk calls. Mathematically, this is because each cell is processed exactly once for both upward and downward pyramid calculations. Each processing step is a constant time operation, so the total time complexity is O rows asterisk calls asterisk O 1 equals O rows asterisk calls. The space complexity is similarly dominated by the DP array and the reversed grid, both of size rows asterisk calls, giving us a total space complexity of O rows asterisk calls. When solving grid-based problems, there are a few common mistakes that can trip you up. First, not accounting for boundary conditions is a frequent issue. For example, if you're working with a grid and try to access indices outside its bounds, you might encounter runtime errors. A good way to avoid this is to always verify that your indices are valid before accessing any grid cells. Next, inefficient brute force approaches can cause time limit exceeded errors, especially with large inputs. Iterating over every possible combination or every grid cell for all potential heights is often too slow. Instead, look for optimized solutions, such as using dynamic programming or prefix sums, to avoid redundant computations. Another mistake is misunderstanding the problem statement. This can happen when you overlook crucial constraints, like ensuring that all cells meet specific conditions for a valid solution. To address this, take time to carefully read and fully understand the requirements before you start coding. Another common pitfall is incorrect initialization of helper structures. For instance, using a DP table or prefix sum array that's not properly sized can lead to logical errors in your solution. To avoid this, make sure you initialize your data structures based on the problem's constraints, and test edge cases thoroughly. Overlooking floating point precision errors is another issue, especially when your calculations involve division or other floating point arithmetic. These errors can lead to inaccurate results, so whenever possible, stick to integer arithmetic or handle precision explicitly. Now, let's consider some insights that can help you in interviews. Recognizing patterns in grid-based problems is crucial. Many of these problems revolve around tasks like identifying regions, calculating areas, or analyzing paths. Spotting these patterns can guide you toward the right approach. Additionally, interviewers often focus on optimization. Demonstrating your ability to improve a naive solution, such as reducing an O(n) squared approach to O(n) with better memory usage, showcases strong problem-solving skills. Finally, always test edge cases like the smallest grid size and all-zero grid, or grids with uniform values, and be prepared to explain the trade-offs between different solutions in terms of readability, space, and runtime. To strengthen your understanding, you can explore related problems that share similar themes. For instance, LeetCode 200, Number of Islands, involves grid traversal and connected components. LeetCode 931, Minimum Falling Path Sum, is a good example of applying dynamic programming in a grid. Another interesting challenge is LeetCode 764, Largest Plus Sign, which focuses on finding the maximum size of a specific pattern in a grid. Finally, LeetCode 85, Maximal Rectangle, is an advanced problem requiring efficient calculations of rectangular areas within a grid. Beyond related problems, it's also worth exploring alternative approaches. Dynamic programming is a powerful technique, offering the benefit of reducing redundant computations at the cost of higher space complexity. This is particularly useful for tasks involving cumulative calculations, such as computing maximum heights or path sums. Prefix sums are another valuable tool. While they require preprocessing, they enable constant time range queries, making them ideal for problems that involve repeated calculations over subarrays or subgrids. Lastly, DFS and BFS are intuitive approaches for traversal problems. However, they can become inefficient if not optimized to handle repeated work. Greedy algorithms offer another approach to solving grid-based problems. These methods are especially effective when local optimization can reliably lead to a global solution. For example, you might use a greedy algorithm to make decisions at each step that seem best in the short term while ensuring they lead to the desired overall result. However, it's essential to recognize their limitations. Greedy approaches can fail in scenarios where exhaustive exploration or more sophisticated techniques are required to account for all possible configurations. Understanding when a greedy solution is appropriate and when it isn't is key to writing efficient and correct code. Great job! Today, we tackled the problem count fertile pyramids in a land, explored its nuances, and arrived at an efficient solution. Remember the key concepts and techniques, as they're valuable for similar problems. Thanks for watching, and I hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!